Imagine for a second that you're doing a load of laundry, right? And you've got this single, heavy, like soaking wet pair of sneakers.
Oh, yeah. That's a classic mistake.
Right. So you toss them into your washing machine, you set it to the spin cycle, and you walk into the other room. And then a few minutes later, it literally sounds like your laundry room is actively being demolished.
Yeah, just banging against the walls.
Exactly. The machine is violently thumping, it's shaking, and it's practically, walking itself across the linoleum floor. So I want you to take that exact same violent, chaotic energy and scale it up. Like way up.
Way beyond a household appliance, I mean.
Right, exactly.
Right.
Imagine that kind of aggressive shaking happening inside, like a 50-megawatt power plant turbine.
Yeah.
Or a massive steel locomotive that's flying down the tracks at 80 miles an hour.
And at those industrial speeds, that shaking stops being just a mere annoyance. It actually becomes a critical safety hazard.
Yeah.
Because you're dealing with these invisible physics that can literally tear heavy machinery apart from the inside out.
And that terrifying reality is our mission for today's deep dive. We are exploring the hidden engineering behind vibration, the standard industry protocols used to prevent it, and the fascinating math that keeps catastrophic mechanical failures from happening in the machines that power our world.
It's a huge topic.
It really is. And the foundation for this journey actually comes from an incredible set of lecture notes and problem sets from the ME 503 Dynamics of Machines class.
Which is such a fantastic resource.
Totally. This material is taught by Dr. Chandan, Chattoraj, a professor in the Mechanical Engineering Department at Dr. B.C. Roy Engineering College in Durgapur. So a huge thank you to Dr. Chattoraj for providing these insights into how engineers are actually trained to handle these massive forces.
Yeah, thank you so much. It really is the perfect starting point. I mean, in the world of high-speed engineering, balancing a machine is a fundamental, non-negotiable safety protocol.
Right?
Without these exact calculations, the modern mechanical world,
Yeah.
everything from jet engines to bullet trains, it simply could not exist safely.
Okay, let's unpack this. Before we can talk about how engineers fix these shaking machines, we really need to understand the root cause, right?
Exactly.
So going back to our washing machine analogy, what is actually happening on a physics level? I remember basic high school physics talking about masses moving in a circle, like when you're on a playground merry-go-round and you feel that invisible force trying to throw you backward off the ride.
Yeah, that invisible force is really the key to all of this. So when any mass rotates, it experiences what we call centripetal acceleration, which is a force directed inward toward the center of rotation.
Okay, inward. Got it.
Right. But Newton's third law dictates there has to be an equal and opposite reaction.
Yeah.
So that reaction is centrifugal force, and that acts radially outwards, pulling away from the center.
Like it wants to fly away.
Exactly. Now, if you have a perfectly symmetrical rotor, imagine just a flawlessly smooth steel cylinder spinning on a shaft. The center of its mass lies exactly on the axis of that shaft.
Dead center.
Dead center. So the centrifugal forces pulling outward are perfectly equal in all directions. The system is balanced. But the danger arises the moment there's what engineers call an eccentricity.
Okay, meaning the center of mass is slightly off-center, just like those heavy wet sneakers sitting on one side of the washing machine drum.
Exactly.
So it's not the actual weight of the machine part that's the issue. It's the fact that the weight is off-center while it's moving incredibly fast.
Yeah, and what's fascinating here is how that off-center weight behaves dynamically.
Mm-hmm.
Because, the magnitude of this disturbing force is constant. Like it pulls with the exact same strength the entire time.
Right.
But because the mass is rotating, the direction of that force is constantly changing. So it might be pulling up, and then a fraction of a second later, it's pulling right, then down, then left.
Oh, wow.
Yeah, and it's doing this hundreds or even thousands of times a minute.
So every time that heavy spot swings around, it is violently yanking the shaft in a totally new direction.
Exactly. And this dramatically increases the loads on the bearings that are holding the shaft in place.
I can imagine.
It induces severe repetitive stress in the metal itself, which causes fatigue and dangerous vibrations.
Okay.
And honestly, if left unchecked, these dynamic forces will snap the bearings, shatter the housing, and literally launch pieces of the machine through the walls.
That is insane. But I'm getting hung up on one thing regarding how engineers actually fix this.
Okay, what is it?
Well, looking through Dr. Chattoraj's notes, the standard industry protocol for balancing a rotating mass is to attach a second mass, like a balance mass, to the exact opposite side of the shaft.
Right.
But if the problem is that this machine already has too much heavy metal swinging around on one side, why is the brilliant engineering solution to bolt more heavy metal onto it? I mean, aren't we just making the engine massive and bulky and terribly inefficient?
It does seem completely counterintuitive, doesn't it? Like, why add dead weight to a machine you want to run efficiently? Well, this is the ultimate engineering trade-off. You see, a lighter, unbalanced machine might seem more efficient on paper, but it will literally destroy its own bearings in a matter of minutes.
Well, that's not very efficient.
No, not at all. But a slightly heavier, perfectly balanced machine, that will run smoothly for decades. So the minimal efficiency you lose in raw weight, you gain back 1,000-fold in operational longevity and safety.
Huh.
You are essentially adding armor against the machine's own physics.
I can accept that trade-off, but I imagine finding exactly where to put that weight and exactly how heavy it needs to be isn't always easy, especially if you have a complex engine shaft with 5 different gears and pulleys, and they're all slightly off-center in completely different directions.
Oh, it gets incredibly complicated.
Yeah.
And that's where the engineering gets highly methodical. I mean, before computers could model this instantly, engineers relied on a specific graphical method, which is detailed in the source material, to solve these complex dynamic balancing problems.
Graphical, like drawing it out.
Yes, exactly. Instead of guessing, they literally draw a forced polygon.
Yeah, I was looking at these polygon diagrams in the notes, and the best way I can describe it to you, the listener, is that it's kind of like giving someone walking directions.
How do you mean?
Well, if you tell someone to walk 10 paces north, then 5 paces east, and then 15 paces southwest, they won't end up exactly where they started, right?
That is a perfect way to visualize it.
Yeah.
Because engineers take all the known unbalanced forces and convert them into a physical length on a piece of paper. So say 1 centimeter represents 10 newtons of force.
Okay, got it.
They draw them head to tail in sequence, pointing in the exact angles those forces pull on the shaft. And because the system is unbalanced, the drawing won't form a closed loop.
Right. The person walking those directions didn't make it back to their starting point.
Exactly.
And that gap between their starting point and their ending point is the exact amount of imbalance in the engine.
Yes. You simply draw a straight line to close that gap. You measure the length of that final line, convert it back to force units, and then you measure its angle.
That's brilliant.
It is.
Yeah.
The opposite of that resultant force tells you exactly how much weight to add and at what specific angle to make the machine run perfectly smooth. It is a highly elegant visual solution to a really chaotic physical problem.
Here's where it gets really interesting, though. Because it's one thing to balance a simple, straight spinning shaft in a factory,
Right.
but Dr. Chattoraj's notes take us into incredibly complex, massive machines with multiple moving parts operating in unpredictable environments, and specifically the engineering behind locomotive trains.
Oh, classic steam and early diesel locomotives are just absolute masterclasses in the physics of balancing.
They are so cool to look at.
They really are, because you aren't just dealing with a hidden internal shaft anymore. You have these massive, heavy steel rods visibly churning on the outside of the wheels, connecting different parts of the drive system together while this entire vehicle hurtles over steel rails.
Yeah, and looking at the history of these designs in the text, they compare a few different train layouts. For instance, in 2-cylinder locomotives, the cranks, the parts connecting the driving pistons to the wheels, are placed at right angles to each other.
Yes, exactly 90 degrees apart.
Right. And the notes say this is to keep the, quote, turning moment diagram uniform. And I'm trying to picture this. Is this essentially like riding a bicycle? Like, if you only had one pedal, you'd push down, surge forward, and then kind of lose all your momentum as the pedal comes back around to the top.
That is exactly the physical sensation. If both locomotive pistons pushed at the exact same time, the train would lurch forward aggressively, then coast, then lurch again.
Which sounds like an awful ride.
An incredibly uncomfortable ride and terrible for traction. But by offsetting the cranks by 90 degrees, it's like having 2 pedals on that bicycle.
Ah.
One piston is always pushing near its maximum power while the other is at its minimum. So it provides a smooth, continuous application of force to the wheels.
That makes total sense. And the notes also break down the physical placement of these components, comparing inside versus outside cylinder locomotives.
Right, which was a huge design choice back in the day.
Yeah. Inside cylinder locomotives have the 2 cylinders tucked entirely away, like hidden in between the planes of the 2 driving wheels under the boiler. Whereas outside cylinder locomotives place them on the outer flanks of the driving wheels, completely visible to anyone standing on the platform.
And then there is the crucial classification of uncoupled versus coupled locomotives.
Right. Explain that one.
Well, If we connect this to the bigger picture of moving a multi-ton vehicle, traction is everything, you know? An uncoupled, or single locomotive, transmits all its engine effort to just one pair of driving wheels.
That seems risky.
It is. If the track is wet, those wheels might just spin uselessly. But in a coupled locomotive, engineers mechanically connect the main driving wheels to the leading and trailing wheels using a massive outside coupling rod.
Okay, so they all spin together.
Exactly. This spreads the driving force across multiple wheels, which gives the train vastly superior grip on the steel tracks.
But adding all those extra churning rods and cranks introduces a terrifying new mechanical problem, doesn't it?
It absolutely does.
Which brings us to, honestly, the most intense part of this deep dive. The danger of partial balancing and the physics of the hammer blow.
Yeah, this is where the math shifts from a manageable rotational puzzle to a highly dangerous dynamic conflict.
Oh boy.
Because in locomotive, you have rotating masses, the wheels themselves and the crank pins going in circles, but you also have reciprocating masses.
And reciprocating meaning the parts moving back and forth in a straight line, right? Like the heavy pistons thrusting inside the cylinder.
Precisely.
Yeah.
And the brutal truth of mechanical engineering is that you cannot perfectly balance a reciprocating mass with a rotating mass.
Wait, really? It's impossible.
It is physically impossible. You can perfectly balance a spinning wheel by adding weight opposite to it. But if you try to use a spinning weight on a wheel to balance a piston that only moves back and forth in a straight horizontal line, you solve one problem, but you invent a catastrophic new one.
Let me think about this. Because a wheel is a circle. Oh, I see where this goes wrong.
Tell me.
When the spinning counterweight is moving horizontally parallel to the piston, it beautifully balances that back and forth thrust, but that heavy counterweight has to keep following the curve of the wheel.
Right.
So when it rotates to the very top or the very bottom of the wheel, it is now pulling straight up or straight down. You've balanced the horizontal jerk of the train, but you've introduced a massive unbalanced force perpendicular to the train's movement.
You nailed it. The train stops jerking forward and backward and instead begins violently pounding up and down on the rails.
Yikes.
Yeah. And because of this impossible geometry, engineers can only perform what is called partial balancing for reciprocating parts.
Partial balancing.
Okay, right. They typically balance only a fraction of the reciprocating mass, say 2/3 of it. They are purposefully leaving the machine slightly unbalanced horizontally to prevent it from becoming completely uncontrollable vertically.
That is a terrifying compromise, and that vertical pounding force has a very specific aggressive name in the industry, doesn't it?
It does.
The hammer blow.
The hammer blow. The effect of this unbalanced primary force acting perpendicular to the line of stroke is a massive rhythmic variation in pressure on the steel rails. It physically hammers the track with every single rotation of the wheel.
Wow. And the sources walk through the math behind the hammer blow, and the physics relationships here are wild. Like, it isn't just a flat amount of force.
Nope, at all.
It relies on the mass of the balance weight, the distance of that weight from the center of the wheel, and crucially, the angular velocity squared. How fast the wheel is spinning.
Yes.
And that squared part is the killer. If the wheel spins twice as fast, the violent pounding force doesn't double, it quadruples.
Speed is the ultimate enemy of a partially balanced machine. Let's look at how that hammer blow interacts with the actual weight of the train.
Okay.
The static dead weight of the wheel resting on the track, let's just call it P, provides a constant downward pressure. The net pressure between the wheel and the rail at any given moment is P plus or minus the hammer blow.
Plus or minus, right? Because when the counterweight spins to the bottom of the wheel, it's smashing down into the rail, adding massive artificial weight.
Exactly.
But when that heavy counterweight spins to the top of the wheel, it's pulling up.
Yes, it is.
Wait, if the upward force from the hammer blow gets stronger than the downward dead weight of the train itself, does that mean this multi-ton solid steel wheel is actually becoming airborne?
Yes.
Are you serious?
I am. If the train gets moving fast enough, that velocity squared term causes the upward centrifugal force to exceed the downward dead weight of the locomotive. The net pressure literally becomes a negative number.
That's insane.
For a fraction of a second on every single rotation, the massive steel wheel physically lifts off the rails. It flies through the air and then slams back down with unimaginable force.
A train wheel lifting off the tracks at top speed is horrifying to even picture.
It destroys the tracks, it shatters the iron wheels, and it can easily derail the entire train.
Oh my God.
This is exactly why locomotives have a strict, non-negotiable limiting velocity dictated entirely by physics, not by engine power. The maximum safe speed of a train is calculated at the exact point where the upward force of the hammer blow equals the downward dead weight.
So it literally cannot go faster.
A train cannot safely exceed this speed even if the engine is theoretically capable of going twice as fast.
It's strictly dictated by this math to keep the train from literally beating the tracks to dust. And,
Yeah.
the notes also mention two other chaotic effects of this compromise.
Right.
There's the variation of tractive effort, which is a residual jerking forward and backward pull because we only partially balance the horizontal stroke.
Yeah, that's unavoidable.
And there's a swaying couple, which is a twisting force that makes the front of the locomotive shimmy side to side on the tracks. You really get a sense of how much violent energy is constantly trying to tear these machines apart.
It is a chaotic environment of interacting forces. And this is why engineering students have to master these specific calculations. They aren't just doing math. They are calculating the survival parameters of the machine.
So how do engineers in Dr. Chattoraj's class actually calculate that breaking point? I mean, let's look at the numbers they have to crunch in one of the exam scenarios provided in the source material. Translating these textbook problems into real-world stakes really highlights what engineers are up against.
Sure, let's look at the single-cylinder engine problem. The setup gives us a reciprocating mass, the part thrusting back and forth weighing 60 kilograms.
Okay, 60 kilos.
The crank is rotating at 60 revolutions per minute. The stroke of the piston is 320 millimeters. We need to find the balance mass required at a specific radius to keep this engine from destroying itself.
And it's funny to look at how engineers are trained to spot hidden traps in these scenarios, because there is a fascinating quirk of engineering terminology here.
Yes.
An engine stroke, which is the total distance the piston travels back and forth, is totally different from the crank radius, which is the distance from the center of the spinning shaft.
This raises an important question of geometry for the students. In our balancing formulas, we rely entirely on the crank radius, not the stroke. And the crank radius is exactly half of the stroke.
Half, got it.
So a 320 millimeter stroke means a 160 millimeter crank radius. If an engineer mixes those two numbers up on an exam, or worse, in a real factory, their balancing math is off by 50% and the engine fails catastrophically.
Wow. So what does this all mean when we run the final calculation?
Well, let's see.
The exam asks the student to balance 2/3 of that 60-kilogram thrusting piston. And when you run the math, equating the forces based on the radius, the answer comes out to 36.57 kilograms.
Think about that scale.
Yeah, an engine part weighing 60 kilograms requires you to bolt almost 37 kilograms of solid dead weight onto the rotating shaft just to stop it from tearing itself apart. You are adding more than half its weight again in pure armor.
And the craziest part, even after adding that massive chunk of metal, the engine still isn't perfectly still.
Because of the partial balancing?
Exactly. Because we only partially balance the reciprocating parts, there is a residual unbalanced force. The notes show that when the crank reaches a 50-degree angle, there is still nearly 210 newtons of force constantly yanking on the engine mountings.
Just ripping at the bolts.
Right.
Oh.
And that tells the engineer exactly how strong the bolts holding the engine to the floor need to be.
The text then scales this exact same logic up to a massive locomotive problem. A train running at 300 RPM with a dead load of 50 kilonewtons, which is over 11,000 pounds of downward pressure per wheel.
Massive forces.
Yeah. Engineers use the exact same principles to calculate the hammer blow, ensuring that those 11,000-pound wheels never go airborne.
Because the foundational physics do not change. Whether you are balancing a small single-cylinder engine in a laboratory or a massive cross-country freight train, it is ultimately a triumph of mathematical calculation over physical chaos.
It really is. It gives you a profound respect for the invisible math holding our world together. Which brings us all the way back to you, the listener.
Absolutely.
Every single time you ride on a high-speed commuter train or even just drive your personal car down the highway at 70 miles an hour, you are entirely entrusting your life to engineers who have meticulously calculated the exact mass needed to stop hammer blows and prevent catastrophic vibrations.
You really are sitting on top of a carefully choreographed dance of physics, balanced down to the millimeter.
Yeah, and it is easy to take for granted when the machine runs smoothly. That smoothness is the result of relentless, precise engineering.
Very well said.
And it leaves us with one final fascinating thought to ponder long after we wrap up here today. Throughout this entire deep dive, balancing has relied entirely on the concept of adding heavy counterweights to physical metal shafts. Like, We fix heavy problems with more heavy metal.
Right, that's been the standard.
But looking toward the future of engineering, what happens to these mathematical models when we start building industrial machines and high-speed engines out of ultra-lightweight materials?
Oh, that's a great question.
Yeah, like if we build an engine block out of advanced carbon fiber or lightweight titanium alloys, will we eventually reach a point where the engine produces dynamic forces so violent and fast that the physical materials of the engine itself are simply too light to effectively counterbalance them?
That would flip the whole paradigm on its head.
It really would. What happens when a machine becomes faster and more powerful than its own weight can handle? Keep that in mind the next time you hear an engine spin up.